Welcome to Session 10 of Lesson 1 of Introduction to Lens Design, and we will be continuing to talk more and more about first-order optics. Need to understand first-order optics before we get into understanding more about the real aberrations in real optical systems. But we talked about the focal points and the principal planes and the principal points, and here's a visualization sort of in an idealized case. Yes, I've added some curvature to the lens, and these rays are certainly well above the axis, so the heights are certainly not in the paraxial region, but had to make it in a scale that we could actually see. But here is some light coming in, collimated light coming into our optical system, which, as we've said, in the paraxial region, by definition, will form a perfect image at the focal point, the back focal point in particular. And similarly, we said that if we have light coming from the front focal point, it will emerge from the optic collimated. Okay, so here is my front focal point, my back focal point. This is a system in air, so the front focal distance is equal to the back focal distance. But again, the focal distances are measured from the principal points. Okay. Now, if we look at this ray trace, again, we're sort of in the paraxial region. So in reality, what we would have expected is when the light hit this surface, it refracted a little bit, and when it hit this surface, it refracted a little bit more. But to isolate the principal planes, rather than looking at the refraction, the change in ray path as the light goes through the component, what we're going to do is just draw the continuation of the light from object space and a continuation of the light from image space, and at the point where those lines, those direction vectors intersect, defines our principal plane locations. And the intersection of the principal plane with the optical axis are our principal points. Similarly, if I take the light coming from a source at the front focus and trace that through the lens, again ignoring refraction, and I take the collimated light from image space, and again ignoring refraction, and trace that straight backwards, where those intersect defines what's called the front principal plane, and the intersection of that plane with the optical axis defines the front or the first principal point. Okay. Again, here is my back focal point, but when we talk about the effective focal length of a lens, what we're talking about is the distance from this principal point to the focal point. We're not talking about the distance from the back vertex to the focal point. That's referred to as the back focal length, but that actually has absolutely nothing to do with the actual focal length of the optical system. And when we talk about focal points, principal points, focal lengths, etc., we can talk about them for a single optical component or for an optical system as a whole. In this particular case, I'm just showing a single element, but I also have principal points, principal planes, focal points, focal planes for an entire optical system as well. The last set of cardinal points I want to mention are the nodal points. And the nodal points are 2 points along the optical axis of the component that basically, if I have light incident at some angle, in this case some angle theta, if the light is directed towards the nodal point, it will exit the system traveling at the original angle, but slightly offset. So you'll notice this light is coming in at this angle theta, and it refracts, and it refracts, but if we were to draw a continuation of that light ray, the point where that ray intersects the axis is the front nodal point. And similarly in image space, if I come back along that ray, and again ignore refraction and just propagate the ray or trace the ray, continue it into the system, where it crosses the optical axis is the second or the rear nodal point. If I have an optical system in air, then it turns out that the nodal points and the principal points are the same. Another very important parameter we use to define an optical system is its power, its optical power. Now when we talk about optical power, what we're talking about is the ability of an optical component to either focus or converge or diverge light. Rays incident on an index boundary at non-normal incidence are going to change direction, and as we've mentioned several times, the ray angle is going to be determined by Snell's law. So you'll notice in this particular case I have a lens that is plano on the back surface, but we still do see refraction. Planar surfaces do not in and of themselves introduce power, but they can refract the rays as long as they're at non-normal incidence. So we see the ray coming in along the optical axis continues to travel at that direction because the angle is zero in both cases. But these rays refract even though planar surfaces in and of themselves do not introduce power. Power, and we typically represent that with the symbol phi, depends upon two things: the change in index at a boundary and the power, and the curvature of the surface. And the curvature is simply the inverse of the radius, so it would be n2 minus n1 over r, but typically we use the c and multiply it rather than divide by r because this is computationally more efficient. We don't end up with a discontinuity at times, so typically we talk about power as a function of curvature. Focal length is the inverse of the power. So in air, the focal length of the system is 1 divided by the power. Notice that the power is dependent upon the change in the index, not the index of the material itself. And again, planar surfaces can refract rays, but they do not introduce power. So if we had a flat mirror, for example, in a system, all we're going to do is redirect the light, but it's going to effectively follow the same path. Need to have both the curvature as well as an index change to introduce power. One of the other approximations we make when we're doing our first order optical calculations is to treat lenses as what are referred to as thin lenses. And what a thin lens allows us to do is effectively, obviously, ignore the thickness. So when we do the power calculation, we only worry about the surface powers. So if we look at the actual power of a real lens that has thickness, the actual power is the sum of the two surface powers, but there is also another term that's a function of the cross product of the two powers, and the optical or reduced thickness, which is the physical thickness divided by the index of refraction. Thin lens calculations ignore this term. So when we're dealing with a thin lens calculation, we simply say the power of the lens is the sum of the two surface powers. What does that do for us? It allows us to make calculations that are a lot simpler, and again, as with most of our paraxial calculations, they're going to be reasonably accurate for the region over which we're performing these first order approximations. Again, first order optics we use to define system properties. We also typically use first order and thin lens type examples, or even paraxial or ideal lens examples, to sort of start our design process. So let's take a look at a simple case. First curvature is 0.1 inverse millimeters. Second curvature is minus 0.01 inverse millimeters. So I've got a symmetric lens. Index 1.5, and let's assume the center thickness is about 10 millimeters. If I calculate the power with the first surface, change in index times the curvature, get this value. Second surface, change in index times this curvature. Both of these happen to be negative values, so again I get a positive value for my power. And here is my thickness term, and here is the cross product term. So if I'm using a thin lens calculation, I simply add up the two powers. Simple enough to do, pick nice easy numbers, which gives me a focal length of about 100 millimeters. If I include that thickness term, that cross term, then what I end up with is my system power is, rather than 0.01, it's 0.0098, which is effectively 101.69 millimeter focal length. Now, if this was my actual final design form, obviously that's a significant difference, an error. But if I'm doing an approximation, I'm trying to see how things fit together, it's sufficiently accurate for my first order type calculations. So often when we do our preliminary design forms, we are going to use this thin lens type calculation. Okay? And we'll talk a little bit more about that in our next session. Thank you.